This video was brought to you by Blinkist.
Forget about that for a second and imagine this scenario.
You're a farmer on the year 500 AD and you're hungry. You have no money, no food, but you do have a field full of wheat. What do?
Well, that's a rhetorical question. You make bread, of course.
You grind the wheat, mix it with yeast and water, and you bake it.
Okay.
But what if you have 8 kids, want to make some money, and don't want to grind all that wheat by hand? In that case, you should probably build a windmill. Now you can grind a truckload of wheat and make a lot of bread.
That is a great idea. And this is a turbine.
The turbine is a rotary mechanical device that rotates when it gets hit by a moving gas or liquid, basically a reversed fan. That can be wind, water, steam, or the exhaust gas from a combustion.
Nowadays turbines are still used to make flour, but their main purpose is producing electricity.
To do that, they can use something as simple as a small DC motor. You attach the turbine to the motor, find a way to make it spin, and you get electricity.
Of course, this setup will only get you so far. To get more juice out of this, you'll need a better turbine, a better generator, and a better moving fluid. And that raises an interesting question. What is the best setup? How can you get the most energy out of a moving fluid? Certainly, the best setup should be the one that is commonly used. And 90% of the world's electricity is produced by steam turbines. A steam turbine is as straightforward as its own name. You basically use heat to boil water, turn it into vapor, and throw the vapor against the blades of the turbine. Okay, but what is the maximum amount of energy a steam turbine can generate? Well, as it turns out, it's not so much about the energy it can generate, but the amount of energy it can convert. On a steam turbine, you transform the heat from burning coal or a nuclear reaction into useful work or movement that spins the electrical generator. This means that you need to put energy in to get energy out. The important factor here is the relationship between the two, and to that we call efficiency. The efficiency of modern bladed turbines is about 90%, and that's brilliant. But modern bladed turbines are quite hard to manufacture. They are comprised of several stages of blades with complex geometry. Luckily, in the beginning of the 20th century, someone came up with an idea that might be a better solution. Of course, I'm talking about Nikola Tesla and the Tesla Turbine. In 1913, one of the most ingenious men to ever walk the face of the earth, aka Nikola Tesla, filed a patent for a steam turbine that he claimed had a 97% turbine efficiency. This turbine was really different from any other turbine designed up until that point, because in its construction, it had no blades.
At first look, a turbine with no blades seems like a car with no tires. And that's because in a conventional turbine, what makes the rotor spin is the pushing force that the fluid impinges on the angular blades. But in the case of the Tesla turbine, the mechanism of rotation is completely different. Instead of using the fluid to push on the blades, the Tesla turbine uses its viscosity to drag a rotor comprised of several thin discs.
Discs? Yeah, discs! Simple circles with a very small thickness.
This is possible due to the boundary layer effect, which is a very fancy way of saying that fluids are sticky. They stick themselves to solid objects, and the thicker they are, the stickier they get. This concept is used on the Tesla turbine by forcing the fluid to flow in a spiral that drags the discs in a circular motion. In this way, the rotor and fluid work in the same plane, so there's no abrupt changes on the path of the flow. Something that doesn't happen in actual turbines, where the fluid and blades work in perpendicular planes, what forces the fluid to drastically change its path.
Now, if after hearing all of this, you're thinking, but in Texas, if the Tesla turbine is the best solution, wouldn't it be used nowadays instead of the conventional turbines? Well, yes. And no. The Tesla turbine is not perfect. It has big disadvantages, like the shear losses at high speed and the low torque output. But just because an idea is not used from the get-go, it doesn't mean it's a bad idea. Electric cars were invented a long time ago, but only now are they receiving the attention they deserve. And that's because someone decided to put in the effort to develop the technology. I'm no Elon Musk, but I'm a very curious punk. So guys, let's put some effort into this. If you follow this channel, you probably know that I have built 2 Tesla turbines in the past. And by built, I mean I 3D printed them. This will be my 3rd attempt at 3D printing a Tesla turbine. And this time I want to make things a little bit different. The first thing that is different is the 3D printing technology.
In the past I used FDM 3D printing, in which plastic is melted and used to draw layer by layer the desired part. This time I will be using LCD 3D printing, in which liquid resin is cured using UV light.
This technology allows for greater precision, which will produce a Tesla turbine with less leaks than the ones before.
To 3D print the parts, I will use my 3 LCD 3D printers, being the first one,
the Resonator.
the second one the Elgu Mars, which will be properly baptized by the end of this video, and the Anet N4, which is a new member of the family and, in my opinion, the most beautiful of them all.
I also want to build a transparent Tesla turbine, or TTT, to run an experiment in which I will run a flow of smoke through the turbine and record it in slow motion. If everything goes right, I will be able to visualize the spiral inside the TTT and get ideas to better design the new one.
To build the transparent Tesla turbine, I used a laser engraver called Ortur Master to engrave my casing design on a piece of plywood. My plan was to trace the path of the casing so I could later use a table saw to cut it out.
There's only one teeny tiny problem with that plan. I don't have a table saw. The only thing I have is a cheap electric saw that can barely cut lines into wood, let alone more complex designs. But anyway, a table saw is just a table with a saw, right? I had a table, I had a saw. How hard could it be? After losing an entire afternoon and a perfectly good table, I am now the proud owner of the crappiest table saw on the planet.
Next, I traced the casing outline on a piece of plywood and I cut it out. I also cut 2 pieces of acrylic that would make up for the transparent part of the TTT. For the inlet I 3D printed 2 parts, an insert for the casing and a Venturi nozzle to suck the smoke in. A Venturi nozzle takes advantage of the Bernoulli's principle, which, badly put, says that when the speed of the fluid goes up, the pressure goes down. The pressure going down means that it sucks.
This is done by constricting the passage of fluid, which speeds up the flow and creates a low pressure zone. 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 Zone.
Zone, zone, zone in the cone. Oh zone, the pressure goes down exactly as is shown. This is just science that should be known. Universal rules that are set in stone. Now stop! I change my tone, speaking the truth into this microphone. I'm turbulent flow, cyclone, destroying lies that I don't condone. Now wait! This music isn't over. Hold down, press the sub button if you wanna hear it moan. Join me! I don't wanna be alone. Peace. After screwing everything in place and cutting out the excess acrylic off, I 3D printed a bracket to find the center of the TTT and drilled the hole for the smoke to be exhausted.
Now looking back, I realize how unnecessary that was, because I could just simply use a marker and a ruler. The casing is a square. I use 3D printing too much. I have a problem. The next step was to find the source of smoke, and what a normal person would do is buy a cheap smoke machine. But me being me, I decided to use cigarettes.
Slepatron.
Now, I am aware of how stupid this idea sounds. Just saying it out loud makes me feel weird. But it's for the benefit of science. Besides, every cigarette that I use here is not ending up on the mouth of an acne-infested 16-year-old teenager.
Slepatron.
I assembled the setup and used an air compressor to push air into the casing. I lighted up a cig and recorded some footage. After taking a look at the footage, I realized the smoke was too thin. Thinking the problem was not having enough cigarettes, I 3D printed a part to be able to use more cigarettes at once.
I called it a cigarette bouquet. I'm not proud. I just hope it works.
Once more I set up everything in my basement and recorded the tests. This is the result. Nothing happened. Except for the fire bouquet at the end, this didn't help at all. I had stupid ideas in the past, but I think this one tops them all. As it turns out, the problem was coming from the Venturi nozzle. The constriction in the middle was making a turbulent flow that was dispersing the smoke. What we need is a smooth laminar flow, and to get that I 3D printed an inlet with a constant cross-section, and I used my lungs.
Now, let me just say that I'm not encouraging you to smoke. Smoking is bad. Very bad. I'm just doing this for science.
As you can see, as the smoke enters the casing, it generates a spiral that moves to the low pressure zone present at the exhaust. In an ideal scenario, we would have a tight spiral that fills the entire casing and goes through most of the disk's surface, but that doesn't happen in this case. In reality, the fluid follows the curvature of the casing, only in the outermost perimeters of the enclosure, and then collapses in the shortest distance possible to the center. This lowers the efficiency of the turbine considerably, and to fix that it's necessary to use a better casing. Luckily for me, Tesla already solved that problem with something called the volute casing.
Nikola Tesla was an amazing inventor, and if you haven't noticed so far, he is also my favorite. Just listen to this. Who springs to mind when you think of the archetypal inventor? For many people it's Thomas Edison. But for others, especially people who have themselves dabbed in inventing, is Nikola Tesla.
This is a quote from the biography of Nikola Tesla by Margaret Cheney. The original book is 422 pages long, and as much as I would like to read the entire thing, between my job, making videos and pretending to have a social life, I just don't really have the time. The text I just read is actually from an app called Blinkist. They transform big non-fiction books into blinks that you can read or listen to in a matter of minutes.
It's cool because it's like a trailer for the actual book, but it still gives you the core message. So far I read the biography of Nikola Tesla, 18 minutes, The Laws of Thermodynamics by Peter Atkins, amazing book, also only 18 minutes, and if you want to know more about 3D printing, I recommend a book called Fabricated, that gives you a rich overview of the technology and its amazing applications in only 12 minutes. That's 3 books in under an hour. That could be a train ride in which instead of staring at Instagram and getting angry that everyone is going to Ibiza except for you, you could be learning and actually enjoying yourself. If you're interested and you want to support my channel, the first 100 people to click the link in the description below get a week of unlimited access to the app for free and 25% discount on a full membership. In a week you can read a lot of books. Trust in Texa and give it a chance. Back to the video.
In a patent filed on 1909, Nikola Tesla explains that the best way to get the highest efficiency out of a turbine is to create a gradual change in direction for the working fluid. To accomplish that, he used the volute casing, an enclosure that gradually decreases its cross-section area and in that way smoothly guides the fluid to the exhaust port.
I never tried this design, so let's see if it improves the end result.
Because the casing is not everything, I also decided to implement a convergent-divergent nozzle at the inlet of the turbine. This nozzle is commonly used in rockets and jet engines to accelerate the pressurized gas to supersonic speeds.
With all the theory out of the way, it's time to start printing some parts.
I 3D modeled the new design and the standard one to serve as a control.
Now is probably a good time to tell you guys that I'm a beginner with SLA 3D printing. And I'm telling you this because I made a lot of mistakes in this project.
For starters, I once again tried to print the axis and discs all in one part. Bad idea. I had to use tons of support material, and that messed up the dimensional tolerances.
I'm not saying it's impossible to print the whole rotor in one go. It's just really hard.
At least it came out better than my last attempt.
I wish that was the only mistake that I did, but it wasn't.
Parts warping, parts unfinished because I didn't put enough resin in the tank, layer shifting, expansion problems, badly cured parts, dimensional failures, using the wrong resin and cutting myself while taking a part out of the printer.
These are all the mistakes that I did, and I hope you are able to avoid them. But after a while I tuned my process.
Beginning at the slicer, it's important to use the recommended curing times. It's also important to orient the parts properly and avoid supports in areas where you need dimensional precision.
Like, for example, the axis of the turbine that needs to fit the ball bearings perfectly to avoid vibration.
After slicing everything, you need to make sure the bed of the printer is properly leveled and all the screws are tight. If everything goes well, at the end of the print you can use a spatula to remove the parts. After that, you should clean the parts with alcohol and put them in the sun for a while, so they finish curing properly.
Since I wasn't able to 3D print the rotor in one piece, I had to redesign the whole thing and print it in two parts, the discs and the axis.
I could only fit 2 discs at one time in the printer, and because I wanted the discs in red and I only had enough red resin for one printer, I used the Anet N4 to print 40 discs. That's a lot of discs, and a lot of prints. In the end, the Anet 4 behaved well. All the discs came out with the exact same dimensions, and it was easy to assemble them on the axis. As supports for the axis, I used 60mm ball bearings, which are capable of reaching insanely high speeds. I printed out both casings and the respective lids, and also one convergent-divergent nozzle and one standard nozzle. I assembled everything, and I used my compressor to make the speed test. I started off with the standard turbine and, using my tachometer, I measured about 15,000 RPM. Then I realized I had the compressor on 2 bars of pressure. I cranked that up to 8 bars and I tested again. Reached a speed of 31,000 RPM, which basically beats the record of my first Tesla turbine by 6,000 RPM. Next, I tested the new design. It only got to about 10,000 RPM. It's not bad, but there was no improvement. I think the reason this design failed was the fact that the volute casing creates a big void at the outmost perimeter, exactly where the flow is more laminar and efficient. The flow goes towards the center in a more gradual way, but at the cost of making the disc smaller in comparison with the diameter of the casing. So for now the standard design still wins. Because it's tradition in this channel, I also tested the turbine using my lungs, and using only the power of my breath, the standard turbine reached the speed of about 6,000 RPMs.
I challenge you to do better.
Because I also recorded some slow-mo footage of the turbine spinning, I was able to compare the results from the digital tachometer with the speed I can calculate using the footage and the stopwatch. It was pretty much the same. Next, I printed a motor support and an axis union which I used to fit a high-speed DC motor on the turbine. I used this and a load of 330 ohms to measure the power output of the turbine. The turbine produced about 7 volts with the load, which gives us a power output of about 0.15 watts.
As you can imagine, this power output can't do much. But that's not my goal anyway. What I really want to do is improve the design bit by bit until I get the best setup. The reason why I bother with this is because I know the Tesla turbine is very versatile and can be of great use. If we put a little bit of effort into this, we can find a way to make energy cheaper and cleaner. For that I count with your support. Leave your opinions on the comment section below. They are of great value to me because, in the end of the day, I'm just some guy with a few printers trying to make a difference. Talking about 3D printers, it's time to baptize the Algoo Mars. On my last video I asked you guys to nickname my new resin 3D printer, and as always you guys rose up to the challenge. You commented a lot of suggestions, but these are my top picks. We have Barsu, which is a fictional name for Mars. The more you know. We have Gooey, Bruno, for obvious reasons, Lil UV, Fred, Goo Lagoon, El Guapo, Printy McPrintface, Marcia, and Igloo Musk. In the end I sent the list with my favorites to my patrons at Patreon, and they chose the name Hell on Mars, which I quite like. If you want to become my patron at Patreon, you can use the link in the description or the panel at the end of the video. Because I now have a new resin 3D printer, I shall challenge you again to find an awesome nickname for her.
All you have to do is post a comment in the video with the nickname and subscribe to the channel.
If the nickname you posted is the one with more likes, and this video surpasses 200,000 views, you will get the printer exactly like this, for free! So don't forget to like, share, comment and subscribe. Well, this is everything for today. Thank you for watching, and until the next time, bye bye!